Good morning, everybody. I will wish first happy birthday to Victor and many happy returns. I should say that I get acquainted with Victor via Volodya Manko, of course. And I have been collaborating with Volodya, as many of you know, for over 30 years. And so obviously I had occasion to look at many papers they had written together. What I would like to do today is to, in very simple terms, try to explain what is the mathematics, what is the mathematical structure behind Schwinger quantum mechanics. Now, as many of you know, most of you know, Schwinger shared the Nobel Prize with Tomonaga and Feynman for quantum electrodynamics. And while he was working on quantization of fields, he realized that very often the quantization procedure is not appropriate. So in some sense, in his vision of quantum mechanics, he decided to start directly with a system which in a sense cannot be the quantum version of a classical one, namely Stern-Gerlach experiment. It's interesting that also Feynman in his lectures made the same choice. So what Schwinger did in thinking about a new foundational aspect of quantum mechanics, he rethought completely the presentation already in his lecture, the academic year 49-50 in Harvard, and then he lectured in Les Houches in 1955, and then some of his main ideas and contributions were published as proceedings of the National Academy of Science. As you know, he was member of the Academy, and so academicians have the privilege of publishing without referees. And this, however, you cannot publish too many pages. Therefore, what he did, he published something like 10 or 15 small papers. And the lectures that he gave in Les Houches eventually became a book which was called The Quantum Kinematics and Dynamics. But when he moved to UCLA, then he lectured again in quantum mechanics, and the notes were elaborated and published posthumously by Bert Angler. And the main text was about the symbolism of atomic measurement. So, as I will argue, essentially, the idea of Schwinger was that you could use, or you should use, a non-classical mathematics to describe the structure of quantum mechanics. And in this sense, it's very close to Dirac in his lectures at Yeshiva when he said, let's proceed at the algebraic level, and only eventually we will identify the variables, what is the meaning, and what is the mathematical structure. So, before entering more mathematical details, let me stress that the description of any physical system, one should identify observables, states, a probability map, which is a pairing between states and observables with various probability measures on R. Usually we consider Borel measures. Then you have to give an evolution, which is either equations of motion or how you move from one state to another. And then you have to give a composition of systems. That is, if you have two systems, how will you describe the composite system? So it's important to take this into account because in the presentation, which actually Schwinger introduced, to take into account this aspect, he somehow mixed up various aspects of the main mathematical structure of his approach, which we identified as a groupoid. Now, the work on groupoid, we started quite early, some 10 years ago, let's say, with a paper with Volodia Manco, Alberto Simoni, Franco Ventriglia, and Cosimo Stornaiolo, and obviously could not be anything else but a groupoidal approach to tomography. So, in that paper, those of you who eventually may be interested in what I am going to say, they will find a friendly introduction to groupoids and further examples. In this talk, I will restrict myself only to finite groupoids to avoid all the technicalities of dealing with the measure spaces, topology of infinite dimensional spaces, differential structure for infinite dimensional spaces, and so on. So, as I was saying, Schwinger had a positivistic point of view similar to the one of Heisenberg. Heisenberg, in his paper, the first famous paper of 1925, he had written, the present paper seeks to establish a basis for theoretical quantum mechanics founded exclusively upon relationship between quantities which in principle are observable. Essentially, he gave up completely the orbits of electrons which had been introduced by Born, and essentially he concentrated on transitions, which are what you actually measure and see. The following up, what Schwinger did was to say again that the laws of atomic physics need to be expressed in non-classical mathematical language. And so we are dealing with the symbolic expression. So starting from here, he introduced the algebra of measurement. So he first introduced selective measurement. You measure A. A, capital A here, should really be thought of a maximal set of pairwise commuting operators. So that when you measure, you get an eigenvalue, we would say. We get a value. And the idea is that after selective measurement, you also have other measurement by which you, what Schwinger expressed, an A prime atom, so for him, we are dealing with the quantum system here are atoms. An A prime atom can enter, and what leaves is an A double prime atom. It is as though the entering A prime atom is destroyed, and in its place an A double prime atom is created. So this was his idea, and he started from these symbols, which have been called M, A prime, A double prime, and gave the algebra of this object. Now, to appreciate the approach by Schwinger, one should stress that in the Hilbert space approach, let's say Schrödinger, Dirac, von Neumann, one essentially associate a Hilbert space with every quantum system, then vectors properly normalized, let's say better rays of the Hilbert space, are associated with states, pure states, and you start from states as primary object, and then you construct observables as operator acting on this Hilbert space, and then the probability function is related to what we usually call the expectation values. Evolution is usually given via Schrödinger equations, and the wave function obviously is as far as possible from something that you actually measure. So in this respect, this approach is quite far from the ideology of Schwinger and Heisenberg. On the other hand, the sister algebra approach, which essentially is the modern version of what was called matrix mechanics, introduced by Heisenberg, Born, Jordan, the primary objects are observables. So you start with observables, then you define the observables are an algebra, it's really a sister algebra, then topological consideration. You introduce actually for Neumann algebras, but these are technicalities which do not interest here us. So out of observables, you introduce states as a dual space of sister algebras with appropriate properties to identify them with probabilities. The other approach, which starts from what I call the third point, that is probability map, may be thought of as the tomographic approach, where you analyze your quantum system in terms of probabilities. And then all of you know how you can reconstruct the states. From the states, you can reconstruct the observables. Let me say that in the sister algebra approach, the refinements were that you can use the GNS construction to actually build a Hilbert space. So you select a state, and out of the state, you build a Hilbert space, which is the GNS Hilbert space. This is interesting because it shows that the choice of the state identifies the Hilbert space. But now the state is prepared in the laboratory. So this means that the Hilbert space that you associate, you construct out of your sister algebra, is really a choice of the observer. So unlike the previous case where the Hilbert space was given, here in the sister algebra approach, it's clear that the Hilbert space is built afterwards when you have chosen a fiducial state. The other approach, which is again in the spirit of Hilbert space, let's say, is what could be called the phase space, and most of you obviously are familiar and have worked on what we now call the Wegener-Weil Moyal Grunewald approach. And in our views, in many papers with Valodia, what we thought of this approach is really a way to immerse, to embed a classical manifold into a Hilbert space. So, in a sense, is a generalized version of coherent states. And we elaborated in this picture with the quantizer to represent the product of observables. But you see from here that essentially the two main approach are Hilbert space and sister algebras. Now, to go to actual measurements, in either case, you have to select a maximal abelian subalgebra of observables, of Hermitian operators. In the approach of Schwinger, the philosophy is quite different. You have essentially the result, what I called earlier, the result of selective measurements, we labeled with A prime, A double prime, and so on. And then you also have to consider the transition from one outcome to a different outcome. So this means that you have objects which are the result of the measurement, and then you define transition from one result to another result. So if you call the result, for instance, what I have written here, the A, I don't know if you can see the pointer. Anyhow, we call the source and the target. So in composing measurements, we find the rules of composition of a groupoid. Now, just a little history of what Schwinger elaborated in his presentation. He started with the simple, which here is MA prime, A double prime, for selective measurement. Then he said, well, this is too cumbersome. So he used a double bar, A prime, and then eventually he came up with the bracket formalism. And in a sense, this captured the idea that an A prime is entering, is destroyed, and in its place, an A double prime atom is created. So in this picture, obviously, if we think of these as rank 1 operators, the action is on the left. The most simple physical example of a groupoid, which is familiar to all of you, is a Grothian term scheme in spectroscopy. You see, the energy levels are the objects, the electromagnetic transitions are the morphism, and you can see all these lines are essentially the morphism or the transitions. And an ordered pair of levels will tell you should be ordered because you have to distinguish transition from absorption. And the main point in analyzing the Grothian scheme by Heisenberg was that he concentrated on the transition. So these levels, which we may symbolize as AJAK, let's say, so the measurement symbols become this rank 1 operator uh, with the vectors which are supposed to be normalized. The normalization is convenient, it's not necessary, but it's very useful if you want to do quickly the computation you need to know. Now, a formal mathematical description of groupoid, finite groupoid, is the following. It is a set whose elements are morphisms, and essentially these are the arrows going from one level to another, or transition. They should be invertible. Essentially, there is not only emission, but also the possibility of absorption. And they connect the objects. Now, morphism and object is a language which comes from category theory. Indeed, another definition of groupoid, which unfortunately would not tell you much, is that a groupoid is a small category in which every morphism is invertible. Now let me be a little, let me introduce some notation. If we denote the objects by X, Y, so Latin letters, in the morphism by Greek letters, there are two maps. So G, script G, will be the groupoid. Omega is going to be the space of objects. So in our previous picture, omega would be the levels, while the elements of G are the transition, which carry the information on the initial point and the final point. So you can define two maps. One is the source, the point where the arrow starts, and the other is the target, which to the transition associate the point where it ends. So this map, which I have defined, are maps that associate with the Greek letter, Latin one, and we have two maps. Now, the composition, as you have seen also from the Gaussian scheme, you cannot compose all transition, but only those which are allowed. There we have to respect the transition with the angular momentum and whatever other quantum numbers may be considered. And so it's clear from there that not all errors can be connected one to the other. But when they are connected, then the composition law is associative. Then you have the selective measurement will end up being associated with unit morphism of the groupoid, and they are the identity, and you have the usual rule. So you see that essentially a groupoid is a generalization of the notion of group. The only thing is that it's not true that all elements can be composed. But when they can be composed, they are associative. So, in particular, with respect to a group, you don't have only one unit, one identity, but you have a family of units, a family of identity. And the family of units may be canonically embedded inside the groupoid by what I have written here. And this immersion, composed either with the source map or the target map, gives you the identity. You have the inverse of a morphism, as I said. With any emission, you also have the possibility of absorption. And then one can define the family of all morphisms whose source is a given point, or the family of all morphisms whose target is a given point. They are denoted by G plus and G minus, and this gives the possibility. You see, if I start with a point X, I consider the inverse image, which means all morphisms whose source is X, and then to every point of it, I associate the target map. When by this association, I cover all the points of the objects of the base space, let's say, then we say that the groupoid is connected or transitive if you think of the action. So in a groupoid, you have a bifibration. That is, you can either consider the fibers as the inverse image of the source, or the fibers as the inverse image of the target. What Schwinger did, obviously, he did not consider the abstract mathematical picture that I have given. He never mentioned groupoid. Groupoid actually at that time had not been invented yet in the form that we have now, and we use them. So what Schwinger did could be considered as a groupoid of measurement symbols. Now, as I already said, they are essentially rank 1 operators. Now, if you arrange, in the case of finite groupoids, them in the form of a matrix where the entry of this matrix are rank 1 operators, then you get an arrangement like this one. And now you see each arrow will connect one element, one vector, let's say, with another one. So it is actually a transition. And it goes from the source to the target. And well, obviously here, because we are used with the action on the right, then we usually write rho by Coulomb product, while Schwinger did the opposite. So one has to be careful if you go to read Schwinger's book. But what is interesting in this picture is now you see that the column going through a diagonal element is what I called earlier G plus, while the row will be G minus. Essentially, rho and Coulomb are related to the fibers which pass through a point which is identified by each diagonal element. So roughly speaking, the elements on the diagonal represent the space of units, or if you like, the space of objects. They are in one-to-one correspondence. While the row and the column, they are the set of transition where one element is fixed. So either the source or the target. Obviously, you can now think of immersing normalized vector in a Hilbert space as rank 1 projectors. And this might be interesting because you see how the groupoid may be related to the Hilbert space picture. Here we have already rank 1 projectors. That is, there is no redundancy neither in the length of the vector, they are normalized, nor in the phase. So these are actually pure states. Um, so you can, as I say here, compose the this transition, these rank one operators with units, and obviously reversing, taking the Hermitian conjugate gives you the inverse arrow. So it is convenient to use a more economical notation for a reason that you will see in a moment. And as Schwinger did, he introduced what he called the probability operator. So diagonal elements of the matrix that I was considering, which are rank one projectors, they are called the probability operators. And now you see that if you conjugate a probability operator with one transition, let's say AJ, EJ, EJ plus one, with a conjugation, you get PJ plus one. So this is a way to go from one rank one projector to another rank one projector. And now those of you who are familiar with the imprimitivity theory by Mackey, we recognize that this is essentially an application of the imprimitivity system. So in a groupoid, what is emerging? That you have units, or if you like, the objects, which are associated with a maximal set of commuting observables. And then you have the transitions, which could be considered as a kind of conjugate maps in such a way that you can move from one to the other. So let me stress, with respect to the Hilbert space approach or the sister algebra approach, the groupoid contains directly from the beginning a choice of a maximal abelian algebra of compatible observables. So what are going to define for you the measurements. The the basic properties are more or less what I told. Now you have to identify states and observables. Now obviously the most simple thing is to consider complex valued function on the groupoid itself, and then by evaluating this function on each one of the elements, you see the writing in the matrix form was instrumental, because now when you evaluate a function on each one element, you get a number, and you get automatically a matrix. So the evaluation of a function on the groupoid on the transition automatically provides you with a matrix. And so now, as we know, if you put appropriate requirements on this matrix, you can define either states or you can define observables. You just have to require the usual property for a matrix to represent a state or an observable, essentially. For the observed hermeticity, for the state, you have the normalization, the positivity, and so in this way we are able to identify states and observables in the space of function, complex valued function on the groupoid. Because of the composition on points when it is available, you can also write a convolution. So you have two structures in a sense. One is what I said in terms of matrices. This would be what is called the groupoid algebra or the convolution algebra. Now, the two are isomorphic. I don't know how much time I am left with. Sergey, could you tell me how much time I have? Well, let me go on. So these two algebras, they are isomorphic, as you can imagine, and but it should be clear that you can either define the convolution algebra or the groupoid algebra. These are this distinction in finite dimension doesn't matter, but when you go to infinite dimension, the situation is important because you have a problem of convergence. Now, this is the way to associate an operator with a function and vice versa. Now, let me stress here an historical fact that Schwinger, in presenting his approach, he did not distinguish the groupoid from the groupoid algebra. Essentially, in setting the postulates or the requirements, he mixed up requirements that one would make on the groupoid with the requirements that one would make on the groupoid algebra. Now, what is the difference? Well, you see, the point is that in the groupoid, the elements are in a sense just entries. Now, to build the algebra, you have to multiply by coefficient to take the sum. Now, the coefficient could be either real, complex. You could also use quaternions. So in essence, the groupoid gives you a subjacent structure which does not depend on which coefficient, in which setting you are later on going to develop your theory. This situation also was present in Heisenberg paper. You see, the composition rule, what we call the Rydberg composition rule of frequency, you see it's already a composition, a groupoid composition, because not all frequencies can be composed, but only those which finish with one which here finishes with K and the other which starts with K. But then what Heisenberg did, sorry, I can't hear you.
You have 2 minutes.
10 minutes?
2 minutes, around 2 and 5 minutes, okay?
Okay. I will finish very soon. So, you see, what Heisenberg did was to introduce also the amplitude, not only the frequencies, to describe radiation. So, essentially, he introduced the convolution product within the groupoid. So, it was only Born and Jordan who said that a way to translate what Heisenberg had done was to introduce matrices. But now, introducing matrices means to go to the groupoid algebra. But now the point is that there are non-isomorphic groupoids which will give the same groupoid algebra. So if I can say in a sentence, Born and Jordan spoiled completely the idea of Heisenberg, who was correctly working with groupoids rather than with algebras. Here is an example for the qubit, because I wanted to show you, but now because I have no time, I will simply skip, but it's clear. The abstract groupoid is what is given in terms of the matrix there. And now if you select a maximal set of commuting observables, you will find the realization which is written here. Now, one important thing is that which is needed in Schwinger treatment is that what I have called E capital E J K, they are also orthonormal. So because they are ortho, you can build a new groupoid. So this is a groupoid out of the previous groupoid. That is here, the the objects which are on the diagonal, they are made up of the previous transitions. So now you have a transition among transitions, but this is what we call either channels or dynamical maps. Uh, Here is another attempt to show that groupoids may be also introduced by taking square root of probability vectors, probability operator, as Schwinger was considering. And essentially, you start with the diagonal. If you take square root, you get either the row or the column, and you may think that the groupoid is really a clever way to take the square root of the diagonal elements. Now, you see why being and becoming. In the groupoid picture, we have the object and the transition among objects, which is a choice which is not available in the other approach to quantum mechanics. And what we have shown in our several papers,
Professor, you have 1 minute left.
Okay, okay, I will finish. I will finish soon. Um, so let me just give you the first paper we wrote with Volodia and Alberto Ibor and others in Naples, which was called the Groupoids and the Tomographic Picture of Quantum Mechanics. And the last one on the web is Groupoid and the Algebra of the Infinite Quantum Spin Chain. And, and that's all, because my time is over. Thank you very much. Many happy returns to Victor. I regret not being there with all of you, but that's life. Thank you.